These are the lesson notes for Algebra 2, and this is for the second day of Section 1.5. This is also the day when we will take a little quiz, and the quiz is basically on Sections 1.2 and 1.3. So we're going to be solving compound inequalities. What's a compound inequality? It means we have two situations that are really happening at one time. And you should remember these from exponential algebra as and or inequalities. So we've got our inequalities here, and inequalities is what we're going to start with first. And means that it has to be in both. So we need to find the solutions that make both inequalities true, not just one or the other. That's an or situation. And means both. So problem 5 says, what is the solution of 7 is less than 2x plus 1 and 3x is less than or equal to 18? So what we're really trying to find is what numbers would make both of those true. And to do that, we can start by solving these. So the first part of this would be solving the 7 is less than 2x plus 1. So I'm going to subtract 1 from both sides, and then I'm going to divide by 2. And when you divide by a positive 2, you don't have to flip the sign. But that looks so goofy when we're trying to graph. So I would go ahead and flip the whole thing around. So bring the x over to the left side and go ahead and flip the less than and make it greater than. So as we're graphing this, we're really graphing x is greater than 3. So we'll put an open dot at 3 and then we'll shade off to the right forever. Now, we can't do the and part of this unless we see what we would also get for solving 3x is less than or equal to 18. So what we're going to need to do with that one is divide both sides by 3. And that is a positive 3, so we don't have to do any flipping of the sign. And 18 divided by 3 is 6. So x is less than or equal to 6. That means we need a closed dot at 6, and we need to shade to the left forever because it's less than or equal to. So now what we need to do is just combine this and say, all right, I have both equations up here. They're both graphed. Where do they overlap? Where are both the graphs occurring at one time? And that would be from here to here. So we try to see what's going on inside that region and realize that our answer has to be true in both. So I start at 3 because that's one end of the overlap that they have. And I notice, yeah, 3 is going to work for this one, but 3 is not going to work for that one. And it has to work for both or I can't include it. So my open dot is going to show that I can't include that point. Now, I know everything in between my two cutoffs is going to work. But now I have to check at my 6. At the 6, should I include that point? Well, it is included because it's shaded for 7 is less than 2x plus 1, and it is included for 3x is less than or equal to 18 because that one has a closed dot. So that one I get to include, and that means it needs to be closed. And of course, we know everything in between. So you can see when they come as two separate statements like this, which isn't very often, what we need to do is think of, okay, where are the endpoints here? Where do I absolutely know only one of these is going to show up? Because that's going to be a stopping point for my and situation. So with both of them, it looks like that. So now I think, well, how on earth could I write that? Well, my solutions are sandwiched in between the 3 and the 6. And the and statements, I actually call them an and sandwich because what that means is our variable is going to be in the middle, and our variable here was x, and then it's going to be sandwiched between the two numbers at the endpoints, the 3 and the 6. And all we have to do is figure out, should we have an equals bar here? Because pretty obviously we're going to use the numbers that are greater than 3, and that's because we can see the shading here, but we have to read this from the middle out. So it'll say x is greater than 3. You read it that way. x is greater than 3. Now, I ask myself if I should have an equals bar, and that is determined by whether or not I'm including the 3. And in this graph, we would not include the 3. Then I go to the 6, and I take a look at that and say, okay, my answers are going to be less than 6. And then ask myself, should I include the 6? Well, this one has a closed dot, so that will be included. So again, you read this from the center out. X is greater than 3 and x is less than or equal to 6, and that's called a compound inequality. And one of our objectives is to be able to solve those compound inequalities. So on the next page, this is a got it, and I want you to go ahead and pause the video and give this one a try. The first inequality is 5 is less than or equal to 3x minus 1. So we would add 1 to both sides and get 6 is less than or equal to 3x. Again, with adding and subtracting to both sides, you don't have to worry about flipping the sign. Then we would divide both sides by 3 and get 2 is less than or equal to x. We divided by a positive 3, we don't need to flip the sign. But for graphing purposes, we probably want to rearrange this, so we'll flip everything in order to do that. That less than or equal to will become a greater than or equal to, and we will get our 2. Now you could certainly just stop right here and just read it backwards, because we start with what are our solutions, and x is where our solutions are at. So you could just read it off from left to right, or I'm sorry, right to left, but that gets kind of awkward for some people. So x is greater than or equal to 2, we would include the 2 because we do have an equals bar, and then greater than or equal to would go to the right forever. Let me switch colors here and we'll solve 2x is less than 12. Well, for that one we just divide by a 2, and that's a positive 2, so that means that we don't have to do any flipping of the sign. And then we want x is less than 6, so we're going to have an open dot at 6, and we're going to shade with an arrow, remember, to show that it goes on forever, to the left. So now what we want to know is, what would the solutions to both of these be? 5 is less than or equal to 3x minus 1, and 2x is less than 12. Well, I can see my endpoints. And remember, it can't just be in one of the graphs, it has to be in both. So as I look at my 2 and I'm trying to figure out whether or not I should include that 2 as an endpoint, I see this is colored in, this is colored in. That means I can color in this dot. That will be included. It is in both of those graphs. Pretty obviously, everything in between here is going to be included, so let's focus on the other endpoint. At the 6, I'm trying to think, well, should I include it or not? Well, it's in this one, in the red one, but it's not in the green one, so I can't include it. I need to have it open. And like I said, obviously everything in between is going to be shaded. And then finally what we would want to do is say x is between 2 and 6. It's sandwiched between those two numbers. And then we see that where we're shading is going to be greater than that 2, so again we have to read that off backwards from inside out, but it also will be equal to it because it is shaded in. It's a closed dot. And then x will need to be less than 6, but that one is an open dot. So that is a compound inequality. That is an and compound inequality. And we did solve that and got her all the way down to where it needed to be. And that's the way we write and statements. It's very rare that we see them written all goofy like they are in some of these, but they're just trying to get across that we can do them this way. So if the variable part of an and inequality matches, we can collapse it and write it immediately as that and sandwich. So notice right here that where the variable is exactly an x plus 1 in both of those situations. So what that means is it is both greater than 5 and less than 13. So we go to the compound inequality of the and sandwich right away. It's sandwiched between the two numbers. And for these, what we have to remember is you still have that algebraic balance. Whatever you do to one part, you have to do to the other parts. So we would go ahead and subtract 1 from both sides. And that would give us 4 is less than x, which is less than 12. But in the end, we know we're supposed to read this from the middle out, so it would be x is greater than 4 and less than 12. So graphing this now, we have the numbers we need. We have the 4 and we have the 12. My number line doesn't quite go out that far, so we would continue that. Again, using the same intervals they have here, they're going by ones every time. That means we have to go by ones every time. That's what I mean when I say that we have to keep those intervals consistent. And then at 4 and 12, we would have open dots because we do not have an equals bar with any of this. And then we'd shade in between because we're making a sandwich. It's like this is a piece of bread, this is a piece of bread. And our answers are the meat, the cheese, all of the good stuff that we're going to put into our sandwich. Or inequalities. Now this is different because this is one or the other, not both. So or inequalities, you need to find all the values that make either of the inequalities true. So either one or the other. And in problem 6 it says, what is the solution of 5 minus 2m is greater than or equal to 21? Or 4m minus 1 is greater than or equal to negative 21. Now, or statements, we don't collapse. You can't collapse an or statement. It's one or the other. So all we do is solve both of the inequalities, making sure that we're careful that if we multiply or divide by a negative that we flip the sign. So let's subtract 5 from both sides and divide by negative 2. And this time, because we divided by a negative, we will have to flip the sign. So it was greater than or equal to before. Now it's going to be m is less than or equal to negative 8. Or, that two-letter little word is really important. And that's because that's what makes this a compound inequality. M is less than or equal to negative 8. Or, all right, now let's go to 4m minus 1 is greater than or equal to negative 21. We're going to add 1 to both sides. So 4m is greater than or equal to negative 20. And then we have to divide both sides by 4, but it's a positive 4. So I don't need to flip any signs there. So that will be m is greater than or equal to negative 5. Now this is not going to be an and sandwich. So we're not going to be shading inside where all the meat and cheese and good stuff will be. Notice the arrows for these two point in opposite directions, and that actually is a huge help when you go to graphing, because we would definitely have a closed dot here. It has that equals bar, and we're going to shade out. The arrow, because the variables come first, show us where we need to go with our shading. And then negative 5, well, that one also has an equals bar, so that's going to be closed, but the numbers that are greater than or equal to negative 5 are going off to the right. These, I always say, we are graphing the extremes. Now, why would I say that? Well, if you want to think about something that's easy to discuss in Minnesota, it would be weather. You know, you think about the extremes in the weather. The extremes would be, hey, we had a day last summer when it's 102 degrees. But you know what? During the winter, we got down to a negative 50 degrees with the wind chill. Those are extremes. And notice how this graph is going to continue on to those extremes. So, and you make the sandwich. You shade in between your two endpoints. But with or, we shade to the extremes. We go out in opposite directions. So the got it here, I want you to take a couple of minutes, pause the video, and see what you get for that one. So, got it, solve and graph or compound inequality. Again, you solve these as two separate inequalities. We would subtract 3 from both sides. So 7w plus 3 is greater than 11. I'm subtracting 3. I do not have to flip any signs. And then I divide by 7, and we notice, oh, this one doesn't work out quite as perfect as the other ones did. No, but fractions happen. It's a part of life, and we move on. We go to the other one and we add 1 to both sides, and we get 4w is less than negative 12, and we divide by 4. Now we just divided by a positive 4, so we don't have to flip the signs. And again, we're going to put an or in here. Now, notice These two are kind of goofy and flipped around because we have W is greater than 8/7 or W is less than -3. I would probably just move them, because then it would make sense that you're looking at those extremes. So we have W is less than -3, an open dot at -3, and then less than going out to the extremes. There's our -50 way out there for our wind chill in the winter time. And then W is greater than 8/7. Well, 8/7 is 1 1/7. I'm going to put an open dot here because we don't want to include that, but I'm also going to label it, and that's because the intervals here did not go by sevenths, so we can't put down what we know to be exactly that position. And then we're going to shade to the right forever. Again, with or statements, always going to happen that you are shading to the extremes. B. And this did not get fixed last year. I thought it did, but there is a mistake in your note packet. This should be reversed. So replace that sign and then pause the video and give this one a try. With the first inequality, we would subtract 1 from both sides. No flipping of the sign with subtraction. Divide by 5. And again, we probably want to flip this one around. And we divided by a +5, so there's no flipping as you're solving the problem. But when you get done, everything just kind of looks backwards. So x instead of less than, greater than 3. Or, and then we go after the second one. We would subtract 9 from both sides and divide by 3. And we have x is less than -1. Now, these again are reversed. We really should write this as x is less than -1 or x is greater than 3. Notice how we always want those arrows pointing in the opposite directions, but we also want them closest to the direction that they're going to go. So x is less than -1 is going to have an open dot at -1, and then we're going to shade to the left forever because these are the extremes when you're doing or. You want to go down as far as you can go and up as far as you can go. And then x is greater than 3, we're going to shade to the right forever. So that is lesson 1.5. And our objectives that we were supposed to achieve, we should have achieved. Those were, we are going to write and solve our inequalities, both in word problems and with non-word problems, and we want to be able to graph them. And we did all of that. So there will be an assignment here for 1.5 day 2. And in class, what you'll do is go ahead and take a quiz and then come back to this assignment. But it is lesson 1.5 day 2, page 38, number 25 to 43, the odd, 44, 45, 47, 51 to 55, 59 to 61, 67 to 69, and 71 to 78. And I realize it's a lot of, just writing down, but that way you're not practicing these problems over and over and over again. Instead of me saying, do 25 to 78, that would have been overkill. You don't need all that. So go ahead and write the assignment down, and after the quiz, this is what you will need to work on.